So with this, I think I'm going to turn it over to Sophie to give you an introduction before we jump into kind of our test case. And please feel free to ask questions as this goes forward. The goal is to be done by 3:15. But again, if you have thoughts after this, as this thing continues to be refined, we sincerely appreciate any emails. Hard questions are completely welcomed. And we understand that this is by no means a silver bullet to this very complicated topic, but it most certainly is, I guess, a line in the sand. So with that is Sophie.
Hi, everyone. Hey, Sophie.
Sophie, can I ask you an orientation question before you launch into the detail?
Yes.
From the forward operating point of view, are you assuming that, or what are you assuming for the old building? It's uninsulated, and did you simply apply that average that you took from for energy consumption for houses?
Henry, actually, to answer a little bit, and not for me to jump in on Sophie's behalf, what they have done is they've created the ability to throttle either test case with more or less efficiency. So it is based upon the average, yes, but you can say effectively that the existing preservation house is 50% less efficient than the average, or 40, 30, 20. It's all dynamic. But maybe, sorry, Sophie, go ahead and explain that.
Good, I'll stop interrupting.
No, please interrupt.
No, that's about right, and I think you'll see more as we walk through the different screens of the workbook that there's a lot of room for the user to actually make those kinds of decisions. So if you look at the version that we have open right now, there are already some numbers in this because we're going to be using it after for Mike to show you actually the demonstration of the 65 Pleasant Street house that he sent the narrative out about. So I'm just going to walk you through the three worksheets and tell you how we came up with this model and this layout and what all of these terms mean. So if everyone can see the screen here, we have the three worksheets are the dashboard, the green building, and the preservation. So just starting on the dashboard screen, what you can see here is this is after you've put in all the numbers, this tells you exactly what the carbon emissions are for the green building versus the preservation. You can see here the lowest emissions will tell you which one is the better option over a given number of years and by how many tons of CO2. And then the year of indifference just tells you, given the rate at which these two buildings are going to consume energy, this is the year at which they would both be equal. And then on the right, you can see we've given the same information graphically. So to give that a little bit more foundation, let's go into the green building model. And the way that we developed this was we started out at looking at existing models of carbon calculators, and we found that there were quite a few for new constructions, but none for preservation. So we used like Mike mentioned, the Athena Eco Calculator, and we also used the greenfootstep.org, which is by the Rocky Mountain Institute, as well as another website called Build Carbon Neutral. And using that, we determined what the major factors are in the construction emissions of a new building, as well as the ongoing operational emissions. And we decided to split the model into two parts based on that. So the left-hand side, as you can see here, is the one-time emissions from construction of a new building. And the right-hand side is the ongoing operational emissions that come from energy consumption of using the building. So the construction emissions are broken down into three parts. The first part is the carbon storage capacity. So all biomass, like grass and trees, anything like that, has the capacity to store carbon over a certain period of time. So using some average numbers, we calculated how much carbon would be released from digging up land or taking out trees, and how much carbon storage capacity would be added by putting in new landscaping or adding new trees. Second, down here you see, starting in cell B11, we have embodied energy of existing structure lost through demolition. So I'm not sure how familiar you all are with embodied energy, but basically this is just looking at the energy that it took to build the existing structure. So everything from the extraction of the raw materials, to turning those materials into building materials, getting them to the construction site, building the house, and even what happens to them after they're taken down and either sent to a landfill or incinerated or anything like that. So this is largely based on the Athena eco-calculator. And so just walking through it, we have different things. We have the foundation wall. Each of these is a drop-down menu. So you can choose, you have a couple options for each one. So if the foundation wall is made out of cast-in-place concrete, you can pick that. And then you enter the number of square feet of that you would be using. And you can see here in D13, it calculates the kilowatt hours of embodied energy that removing 1,000 square feet of cast-in-place concrete from the foundation wall would incur. And then up here in cell D11, that then summarizes all of the embodied energy that's lost through the demolition and converts it into CO2. So you can see all the different options. We have foundation slab. For that one, we just have the one choice. Foundation footing, also just one. And then it gets a bit more complex as you go into these other options. So intermediate floors, you have about a dozen options. The window frame. The window frame is actually looking at the embodied energy of the window, and it's just it sort of assumes that you have this double-paned argon windows, and then they just want to know what kind of frame it's in, and so forth. Down here, you have 5 options for miscellaneous materials. So these can come in quite handy when we get to the preservation, when you have these sort of materials that might not be as commonplace as today's materials. So if you have a house made of clay and bricks, you could pick, is it 12-inch blocks or 4-inch, and then enter the number of square feet in total. For some of these options, they're actually in cubic feet. So, for example, rubber, when you pick that, this cell here turns into cubic feet, and you enter the number of that, and it, again, returns the kilowatt hours and is then converted to CO2. And then the final thing that you have for the new construction is actually the bringing in of the new materials for the new building. So this is whatever's going to go in. So the new foundation, the new walls, new carpets, all of those things. And so the sum of those 3 things gives you the total one-time carbon emissions, and that will be added up here in cell I-21. On the right-hand side, what we have is the operational emissions. So this is once the house is up, how much energy is it going to consume every year? And we base this on 2 factors. The first is the region, and the second is the size of the house. Region, it's sort of broad-based. So, for example, this house that we're going to be looking at today is in New England, and it's 2,800 square feet. And so we looked at the Department of Energy, average energy consumption for houses in all these different regions, and we also looked at the average energy consumption per square foot of a house. And based on those 2 numbers, we get an average. This is how much a 2,800 square foot house in New England would consume per year on average. Then we have the option of doing added efficiency. So this is where Henry is asking, how do we determine how efficient this house is? Well, if you're building a green building, it has to be at least 15% more efficient than an average house to be considered green, but it could be as much as 40 or 50%. So you have the option of just stating that here. Also, with a green building, you might be generating energy on site, either through solar panels or some other method, or you could be purchasing renewable energy. So you have the option of just putting in a fraction here. And then finally, we have the carbon coefficient. So you pick the state that you're in, or for some states there's more than one option. And what this does is, based on the utility mix of that state, gives you the coefficient that you would multiply the kilowatt hours by to determine the total tons of CO2 emissions. So a state like Massachusetts might use more hydropower or solar power than a state like Texas. So the carbon coefficient is going to be lower for Massachusetts. And then finally, we have this option, expected building lifetime. And this is actually just the number of years that you want to compare these 2 buildings over. So it just gives you the length of time that you want to look at. So in this example, we're going to use 50 years. So here down in I-23, you can see that we've summarized this. The total one-time emissions would be about 1.8 million, and then emissions per year are 6,700. Over 50 years, the total is going to be over 2 million tons of carbon. So before we go into the preservation models, do we have any questions?
Yeah, how do you determine the lifetime number?
Right. So I think maybe the name of this cell was a little bit misleading, and I didn't have a chance to rename it in advance of this meeting, but it's just the number of years that you want to compare over. So, it's not necessarily how long you think the building will last, but it could be that. So if you're thinking we want to look at this as a 50-year investment or a 20-year investment, then you would just pick that number.
Okay.
It just gives you a base number of years to compare over, but it's not saying that in 50 years we're going to definitely tear down this building again.
Okay.
Other questions so far?
I had one question. You ran through the preservation model once, didn't you, in terms of embodied energy? And when you got to windows, you were talking about double glazing. I got lost there.
Okay, so the embodied energy section, so this is the stuff that you're going to take out of the existing building. So it's the energy that's embodied in that house that's already there. And we assume that when you're going to do a demolition and put up a new building, you're probably going to take out everything that's already in the existing structure, whereas in the preservation, you're only going to be taking out some of what's in the existing structure. And for the windows...
Why is... Oh, because you're keeping it. I don't get it. Lost through demolition. I thought that meant you were erasing the building from the world.
In this case, Henry, on this screen, we are actually erasing the building from the world.
Yes.
So we're kind of looking at two ways. It's a model that is very focused on the decision point where you have, let's say, a 65 Pleasant Street of the world. And you say, we are going to knock this down and build a comparably sized, very efficient building in its place, which is the screen you're seeing now.
Yeah.
The screen we're going to advance to is we are going to tear pieces of this building out and replace those pieces with preservation materials. And I think the underlying your question is a very important aspect of what materials are used. And something we initially kind of ran into the problem is there's no way for the Athena Institute to calculate carbon impacts of materials from 1802 and the actual life cycle process of sourcing and refining and installing those materials. And that is an interesting question. We feel this model controls that a little bit because the inputs we're using are likely less green. I mean, the idea of oriented strand board, Arkansas, hopefully has more of a carbon consequence than sheathing that was hand-sawn on site and field stones from nearby foundations. That, of course, is a very gross assumption on our part. So recognizing that we don't actually have carbon consequences for single-pane leaded glass is an issue.
I think one of the smartest things you've done, and incidentally, I'm extremely impressed by this, but one of the things you've done that's really healthy is begun to generate a list of things that could be added to Athena's eco-calculator.
Well, there's value in the process because, Henry, we did discuss a lot about some of your early points about how this is just, the interrelationships become so complex, and I think that the team has really tried very hard to do things like capture on-site generation or the regional composition of different energy sources, whether that be coal or hydro, and efficiencies. And those are captured in multipliers and ratios that I think are subject to a great deal of debate. But that was sort of part of the assignment was we didn't want them to answer those questions, recognizing that that would be impossible for a team of 4 students to do in a semester. Instead, we wanted to come up with just a model that at least represented the relationships among them so that other people down the road with better information can then put in better inputs. I mean, the model, like all models, is garbage in, garbage out. And so if we're hoping that the better the data we have, the better the answer we get.
No, I think it's fantastic. I am impressed and intrigued that the embodied energy is as high as it is.
Honestly, I think that's something that we're going to have to probably to filter through. But because I want to actually record these questions, so before we get to that, Sophie, do you want to continue with the rest of the model?
Sure. So now I'm going to go over to the preservation tab, and